A customer clicks the purchase button once, but your database records two identical charges due to a transient network failure. This creates immediate financial discrepancy and customer distrust. Standard retry logic in modern applications often triggers a second post request when the first attempt exceeds a socket timeout, despite the server potentially having already succeeded. Network timeouts are frequently false negatives. The backend finishes the transaction, but the acknowledgement never reaches the client, leading the sender to assume a total failure occurred. An operation is idempotent if performing it multiple times yields the same result as a single execution. While get and delete are naturally idempotent, post requires manual implementation. The idempotency key is a unique value generated by the client to identify a specific intent. It allows the server to recognize and ignore subsequent identical requests. Clients should generate a universally unique identifier, version 4, before making the call. This key must be persisted locally to ensure the same key is reused during retries. The key is typically transmitted in a custom hypertext transfer protocol header, such as idempotency-key. This keeps the business payload clean and separate from request metadata. Upon receiving a request, the server first checks a fast access storage layer, like Redis, to see if the provided idempotency key has been processed recently. If the key is new, the server records it with a status of started. This prevents other concurrent requests with the same key from initiating the same business logic. When a second request arrives while the first is still processing, the server should return a 409 conflict status code to inform the client to wait.
Checking for the key and marking it as started must be an atomic operation. Use set if not exists commands in distributed caches to avoid race conditions between threads. Once the lock is secured, the server executes the core business logic, such as charging a credit card or updating a ledger within a standard database transaction. After the logic completes, the server must store the full response body and the status code alongside the idempotency key before releasing any locks. When a retry arrives after a successful completion, the server finds the stored response and returns it immediately without re-executing any business logic or side effects. The returned response must be identical to the original. This includes the same body and same status codes, ensuring the client cannot distinguish the retry from the original. To prevent key reuse for different operations, generate a cryptographic hash of the request body. Store this hash with the idempotency key to validate request consistency. If a request arrives with an existing key but a different payload, the server must reject it. This indicates a client-side error or an attempt to reuse keys. For payload mismatches, return a 422 Unprocessable Entity status code. This clearly signals that the idempotency key is already tied to a different set of data. Idempotency keys should not be stored forever. Implement a time to live of 24 to 48 hours, which covers the typical window for automated retries. Redis is ideal for idempotency storage because of its sub-millisecond latency and built-in support for key expiration. It handles high throughput with minimal architectural overhead. Storing the key in your relational database ensures strict consistency. You can save the idempotency record and the business data within the same atomic commit.
In a microservices architecture, use a distributed locking library like Redlock. This prevents multiple instances of a service from processing the same key at the same time. The business logic and the idempotency state update must be inseparable. If the business logic fails, the idempotency key must not be marked as completed. If using a relational database without native time-to-live support, schedule a recurring background job to delete old idempotency records to prevent table bloat. Stripe popularized the modern idempotency key pattern. Reviewing their documentation reveals a robust implementation that handles millions of transactions daily without duplicates. An Internet Engineering Task Force draft exists for the idempotency-key header. Following this emerging standard ensures better compatibility with future third-party gateways and proxies. Keys should be scoped to a specific user or account. This prevents accidental collisions where two different users might happen to generate the same random identifier. If your server encounters a 500 internal server error, do not save a successful result. The client should be allowed to retry the same key again later. Idempotency is equally vital in asynchronous systems. Message consumers should use the message identifier as an idempotency key to handle at least once delivery guarantees. True exactly once processing is nearly impossible in distributed systems. We achieve the same effect by combining at least once delivery with idempotent processing logic. While idempotency adds a lookup step, it reduces overall load by preventing expensive duplicate operations. The performance cost of a Redis check is negligible compared to a duplicate payment. Clients must persist the key in durable storage before the first network attempt.
If the app crashes, it must recover the key to retry the same logical transaction.
Without persisting the key locally, a mobile app restart would generate a new key for the same purchase, bypassing the idempotency check and causing a duplicate charge. Intermediaries like load balancers or gateways may retry requests automatically. Ensure your entire infrastructure respects the idempotency-key header to avoid internal duplication. Collision risk for a 128-bit universally unique identifier is practically zero. However, combining the key with a client identifier provides a secondary layer of safety. Do not use predictable keys like timestamps or incremental integers. If an attacker can guess a key, they might be able to view or interfere with another user's transaction. Include the idempotency key in your server logs. This allows support teams to trace a client's retry history and verify if a response was served from cache or processed fresh. Be careful when caching error responses. If a request fails due to a temporary validation error, caching that error will prevent the user from fixing and resubmitting with the same key. Implementing idempotency requires a dedicated storage strategy and logic in the request pipeline. For critical financial or state-changing operations, this overhead is a mandatory requirement. Many modern frameworks offer middleware or decorators to handle idempotency boilerplate. Explore libraries for Spring Boot, Node.js, or Go to accelerate your implementation. Unlike e-tags, which are used for optimistic concurrency control during updates, idempotency keys focus strictly on the safe retry of an operation that has no known current state. The robust idempotency strategy involves client-side key persistence, atomic server-side locking, and durable response caching. This combination eliminates duplicates and ensures a seamless user experience.
Start by identifying your most critical post endpoints. Apply the header check, implement a fast lookup in Redis, and ensure your business logic remains wrapped in clean transactions. Mastering idempotency keys transforms your API from a fragile system into a resilient enterprise-grade service. This prevents data corruption and saves countless hours of manual reconciliation.